In section 5 of chapter 20, we're going to be looking at how free energy relates to the cell potential. And it's a pretty straightforward relationship. So our formula that gives the relationship between the change in Gibbs free energy and the cell potential is this. Delta G is equal to negative N F E, where N is the number of moles of electrons that are transferred. I'll show you how to determine that here in just a moment. F is the Faraday constant, and that's the 96485 coulombs per mole of electrons. We saw that. Did we see that earlier? We're going to talk about this in more detail. And then E is the EMF, or the cell potential of the reaction. So that is how we calculate delta G. Now, if it happens to be at standard conditions, then delta G standard is equal to negative NF E cell standard. So pretty straightforward calculation there. So the trick is just coming up with N and the E cell standard. F, the Faraday constant, that is a constant that relates the number of coulombs to the number of moles of electrons. That's just a value that has been determined. So we have 96,485 coulombs per mole of electrons. All right, so let's look at an example calculation. All right, so we'll start with determine the E cell standard, delta G standard, and the equilibrium constant for this reaction. So 2 moles of aluminum ion plus 3 moles of calcium gives us 2 moles of aluminum metal plus 3 moles of calcium ion. First things first, we want to calculate the E cell standard. To do that, of course, we'll look at the 2 half reactions. And so aluminum ion getting converted into aluminum metal. That's the reduction, so that must be the cathode here. Our reduction potential here is negative 1.66. That is determined from Appendix E. So you can get that value from Appendix E. For calcium, calcium getting converted into calcium ion, that's an oxidation, so that's the reaction occurring at the anode. And that one has a value of negative 2.87 volts. So when we do cathode minus the anode, we will get E cell standard is equal to negative 1.66 volts minus negative 2.87 volts. And make sure you pay attention to that minus negative. And we'll get 1.21 volts. So 1.21 volts is our E cell standard. To get delta G, we're going to need to determine what the value of N is. Well, N is the number of moles of electrons that are transferred in the balanced chemical equation. Remember, in order to add these two half reactions together, we had to multiply them, and you'll see we got these coefficients as a result of that. So we have to multiply them so that these are the same number. And we want to get it so that these two, we increase them to their least common multiple. The multiples of 2 are 2, 4, 6, 8, 10. The multiples of 3 are 3, 6, 9, 12, and so on. The smallest number on both of those lists is the least common multiple, and that value is 6. So N is going to be 6. So, and that's how we determine what N is. So now we'll calculate the delta G standard from E cell standard. All right, so there is our formula, negative NF E cell standard. N, as we mentioned, is 6 moles of electrons. The Faraday constant, 96485 coulombs per mole of electrons. You'll see the moles of electrons cancel out. And then our E cell, 1.21 joules per coulomb. A volt is a joule per coulomb. I wrote it like this so that the units cancel out, and we'll get our answer in joules. That gives us an answer of negative 7.00 times 10 to the 5th joules. So negative 7.00 times 10 to the 5th joules. All right, so that is that. Normally for delta G, we would stop here and we would convert that into kilojoules. And so pay attention when you're working a problem like this. It may ask you to convert it into kilojoules. But since our next thing is to calculate the equilibrium constant, we're going to have to convert it back into joules anyway, so I'm just going to leave it like this. So now we'll calculate that equilibrium constant, KEQ. KEQ for this reaction, so we've got delta G. KEQ is going to be equal to E to the negative delta G standard over RT. And so we'll put that value in. R is 8.314, and the temperature is 298. In this chapter, we're going to assume 298 unless it is expressly, no, we're just going to assume 298. We don't have any of our electrochemical calculations in this chapter at different temperatures. Some of the assumptions get a little weird when we do that. So, all right, so we put all those numbers in. So negative of a negative, make sure you pay attention to that. That will give you a positive value. We'll get E to the 283, and that gives us a value of 6.1 times 10 to the 122. That's probably too many sig figs because of our rule of sig figs with exponents. However, if you punch this into your calculator, you're probably going to get an overflow error. So most calculators that are typical, like the TI calculators, they'll give an overflow for anything that is over 10 to the 100. So I made sure that on the test we don't have any that are going to go over 10 to the 100. So we want to look at number 47 on the in-class assignment. So we're going to switch over to our document camera here. And so here we've got this problem. And you'll see we've got several different half reactions that are written here. And it says, write the balanced chemical equations for the oxidations of iron 2 by dithionate and for the oxidation of iron 2 by hydrogen peroxide. Well, we're going to start with this one, and then we're going to do this other one on the back of this page. So it says calculate Ecell standard and delta G for each reaction. That'll be easy enough to do because we've got our reduction potentials here, and then calculate the equilibrium constant K for each reaction. So we'll start by writing out the chemical equation. So we're going to do the half reactions first. And so for the half reactions, we've got Fe2 plus Aq, and we're oxidizing Fe2 plus Aq, so it's going to go the opposite direction. So it'll be Fe3 plus Aq plus an electron. The reduction potential is still going to be the same value, so 0.771 volts. All right, and then for the dithionate, so we'll get S2O6 2 minus Aq plus 4H plus Aq plus 2 electrons, and then that gives us 2H2SO3 Aq. And that has a reduction potential that is equal to 0.564 volts. Now, in order to add these two equations together, this has one electron, that has 2. We're going to have to multiply that top equation by 2. But remember, we don't multiply the reduction potential, we just multiply the equation. So when we add those together, the electrons are going to cancel out, so I'm not going to write those. We will get 2 Fe2 plus Aq plus S2O6 2 minus Aq plus 4H plus Aq gives us 2 Fe3 plus Aq plus 2 H2SO3 AQ. And I'm going to make sure everything's balanced here. I've got 2 iron, that works. 2 sulfurs. Oxygen, we've got 6, and then 2 times 3, that's 6 there. And then hydrogen, 4 and 4, and then our total charge, positive 4, negative 2, positive 4. So that gives us a total of positive 6. And then 2 times 3 is positive 6. So that is a balanced equation. It's always worthwhile to go through and make sure that it is actually balanced. And now we will calculate Ecell standard. And Ecell standard is going to be the cathode minus the anode. Our cathode is this, so it's 0.564 volts minus 0.771 volts. Now you'll notice here something interesting that occurs, and that is that we're going to get a negative value for our Ecell standard. That tells us that this reaction won't be spontaneous in the forward direction. That's okay. It's not like we're trying to literally do this reaction. We're trying to determine what the equilibrium constant is. So we're going to take that value. So we'll do 0.564 and subtract away 0.771. And that gives us negative 0.207 volts. So that is our Ecell standard. All right. From that, we can get delta G standard. So I'm going to go ahead and that was one of our main goals, was to get that Ecell standard. So now we'll do the delta G standard. So delta G standard is equal to negative NF Ecell standard, and that's equal to negative the number of electrons. We had 2 and 1, but we multiply this, so that's 2. So negative 2 moles of electrons times 96485 coulombs per mole of electrons, and then negative 0.207, and a volt is a joule per coulomb. And again, I'm writing it that way so that our coulombs will cancel out and we will get our answer in joules. So I'll take that negative 0.207. We're going to multiply that by 2 and multiply it by 96485. And with 3 sig figs, we're going to make that negative 3. We also have to multiply that by negative 1. So I'm going to multiply that by negative 1, and that will give us a positive answer there. So we're going to get our answer here as 3.99 times 10 to the 4 is our joules, is going to be our value for delta G. Now, like on the problem we did in the presentation, normally we would convert that into kilojoules, so we would divide that by 1,000 to get it as kilojoules. However, we're about to use this in our calculation of our equilibrium constant, so I'm not too concerned about it. So now, let me scoot my paper a little bit. So we've got our equilibrium constant, KEQ, is equal to E to the negative delta G standard over RT. So E to the negative 3.99 times 10 to the 4th, and then 8.314 and 298. All right, as long as this is in joules, this will all work out. So now we'll take that number, and I'm going to go ahead, and since we have a negative there, I'm going to go ahead and multiply that by negative 1. Actually, I'm just going to re-enter it. So negative 3.99 times 10 to the 4th. We're going to divide that by 8.314, and we'll also divide that by 298. And you'll see that gives us 16.10. So, or negative 16.10. So e to the negative 16.10. And so now we're going to take that number and evaluate it. So I'll do second exponential function. We'll grab that answer. And you'll see we're just going to call that 1.0 times 10 to the negative 7. And that is the value of our equilibrium constant. So that's how we take reduction potentials and calculate equilibrium constants. Now I'm going to do the second one, and to kind of help you guys get this set up. The way I'm going to do that is I'm going to show you how to set up the two equations. Again, we're oxidizing iron 2. So we're going to have iron 2. And the iron 2, Q, is getting oxidized to form iron 3 plus an electron. We already know that that has a reduction potential that is equal to 0.771 volts. And then hydrogen peroxide is going to be our oxidizing agent. So plus 2H plus 2 electrons. And that gives us 2 H2O liquid. And that has a reduction potential of 1.776 volts. All right, so that should help you get it set up. I'm going to pause for a second. This will give you an opportunity to pause the video, go through and answer it, and then you can restart the video once you have figured it out. Okay, so now before we can add those two equations together, we'll need to multiply that top equation by 2 so that we can get the same number of electrons. And so now we'll put everything in there. So we'll get 2 Fe 2 plus Aq plus H2O2 Aq plus 2H plus Aq. The electrons cancel out, so I'm not going to write those. We'll get 2 Fe 3 plus Aq plus 2 H2O liquid. And I'm going to double check to make sure everything cancels out. So we've got 2 irons, 1, 2, 3, 4 hydrogens, 2 oxygens, and 2 oxygens, so all the atoms. Positive 4, 0, and positive 2, that gives us positive 6, and then 2 times 3 is positive 6. So that is a balanced redox reaction. So next, we'll calculate the Ecell standard. And Ecell standard is the cathode minus the anode. And in this case, we are going to get a positive quantity, so 1.776 volts minus 0.771 volts. And that, of course, gives us 1.005 volts. So that is our Ecell standard. Go ahead and highlight that to indicate that we got that. So now what we want to do is to calculate delta G. All right, well, delta G is equal to negative N F Ecell standard. And our number of electrons here was 2. All right, so 2 moles of electrons. So we'll put negative 2 moles of electrons. And then 96485 coulombs per mole of electrons. And then 1.005 joules per coulomb. And our moles of electrons cancel out, and our coulombs cancel out. And so now we'll multiply all that out. So I'll do, let's see, negative 2 times 9,6. All right, make sure this is all on here. So times 9,6,485 times 1.005. And that gives us negative 1.939. We do have 4 sig figs here. So negative 1.939 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th joules. And delta G here is negative, and that makes sense because Ecell was positive. When Ecell is positive, it'll be spontaneous in the forward direction. When delta G is negative, it also means it'll be spontaneous in the forward direction. So there is our delta G. So next, we'll put that into our formula for the equilibrium constant. So KEQ is going to be equal to E to the negative delta G standard over RT. So we'll have E to the negative 1.3 or 939. I'm going to fix that real quick. That looks ugly. So 1.939 times 10 to the 5th over 8.314 times 298. So negative of a negative. And so I'm going to multiply that by negative 1. So times negative 1. And I'm going to go ahead and just punch that in again. So we'll do 1.939 times 10 to the 5th. And we're going to divide that by 8.314. And then we'll also divide that by 298. And you'll see we get 78.26. So that gives us E to the 78.26. So now we'll just do second E, and then we'll grab that answer, and that gives us 9.75 times 10 to the 33. So 9.75 times 10 to the 33. We really only have 2 sig figs there, so instead of calling it 9.75, we're going to call it 9.7. So we'll call that 9.7 times 10 to the 33. And that is the value of our equilibrium constant. So you'll see that when we have a negative value for delta G, that gives us that'll give us a value of K greater than 1. When we had a positive value for delta G, we had an equilibrium constant that was less than 1. Okay. So we'll go back over to our presentation. And we're going to look at electrical work. And so for electrical work, we want to see how much electrical work it is. Now you may remember, so here is our equation. You'll see here we've got the question, determine the maximum amount of electrical work that the following reaction can produce when 205 grams of aluminum is produced. So when this process occurs, if we could somehow harness this in a battery, how much electrical work could we potentially do? Well, we know that delta G standard is going to be equal to negative work max. So that means that work max is negative delta G standard. But that delta G standard is per 2 moles of electrons. So that's the so this will be 7.00 times 10 to the 5th joules per 2 moles of aluminum, not electrons, 2 moles of aluminum. And so this is as per the reaction. If it was how much, if it was how much per mole of calcium, this would be this many joules per 3 moles of calcium consumed. Okay, So if we take the 205 grams and we divide by the atomic mass of aluminum, the average atomic mass, that will give us the number of moles of aluminum, and then we can multiply by 7.00 times 10 to the 5th joules per 2 moles of aluminum. So the moles of aluminum and the grams of aluminum cancel out, and we will end up with 2.66 times 10 to the 6th joules. Now, if you're thinking, well, how much electricity is that? Like how much would I have to pay my electric company for that? And if you look at your bill, they do not charge you in joules, right? They don't charge you per joule, like some number of cents per joule. Well, first of all, a joule is a really, really small unit of energy. And so the unit of energy that is preferred by the electrical companies is going to be the kilowatt hour. And that's a kind of an unusual thing, but it's just how electricity is measured from the electrical company. So let me show you how to convert that into kilowatt hours. And we'll start by saying what a watt is. A watt is a unit of power. It tells us how much energy is used per unit time. In particular, it tells us how many joules are used per second. So 1 watt is 1 joule per second. That means a kilowatt is 1,000 joules per second. A kilowatt hour is 1,000 joules per second times 1 hour. So if we multiply 1,000 joules per second times 1 hour and then convert the hours into seconds, that way we can cancel out the seconds and the hours, that will tell us how many joules. So the number of joules in a kilowatt hour is 3.6 times 10 to the 6th joules, so 3.6 million joules. So now all we need to do is use this conversion factor that 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules. So we'll do the 2.6 times 10 to the 6th divided by 3.6, or 2.66 times 10 to the 6th divided by 3.6 times 10 to the 6th joules per kilowatt hour, and that gives us 0.739 kilowatt hours. And so now we're going to look at number 88 in the in-class assignment. All right, so here is number 88. We've got this system where we've got zinc plus copper 2 gives us zinc 2 plus copper metal. And so this is one that we had done earlier. I'm going to go ahead and up here at the top, I'm going to go ahead and write out the 2 half reactions so that you have them. But zinc solid is getting oxidized to form zinc 2 plus AQ plus 2 electrons. And the reduction potential, I don't remember the value of that reduction potential, but we'll grab that here in just a moment. And then for copper 2, we've got Cu2 plus AQ plus 2 electrons, and that is giving us copper solid. And we will look up that value here in just a moment as well. So here I'm going to go ahead and go over here. Oh, look, there's zinc. Zinc is negative 0.763 volts. And copper, I think copper is up here. There's copper. So copper to 0.337. So now we will go back. All right, I think I maybe didn't show you the Appendix E. Anyway, there it is. So I looked those up on Appendix E in case you were wondering, where did I get those numbers? All right, so Ecell standard is going to be equal to 0.337 volts minus negative 0.763 volts. And that gives us 1.100 volts. So that is our cell potential. All right, so under standard conditions, what is the maximum electrical work in joules that the cell can accomplish if 50 grams of copper is plated out? What is that quantity in kilowatt hours? So we have our Ecell standard. So we're going to do delta G standard. So delta G standard is equal to negative NF Ecell standard. And N is the number of electrons. This one, it's pretty easy. There are 2 moles of electrons. So I'm going to put I'll put negative 2 moles of electrons. And then our Faraday constant, 96485 coulombs per mole of electrons. And then we'll multiply that by the 1.100, and instead of volts, I'm going to write that as joules per coulomb. And that way our units cancel out properly. And that's going to give us our answer in joules, and that will give us a negative number. So we'll do negative 2 times 96485 times 1.100, and that gives us, let's see, we've got 4 sig figs there, so we're going to call that negative 2.123 times 10 to the 5th joules. All right, so that is our delta G. But this is per mole of copper. I'm going to put that as a little note here. This is per mole of copper. And the reason that we know that is that it's per the reaction. So, it's this many joules as per the reaction. So that's per mole of copper. So that means that our W max is going to be the negative of that negative. So W max is going to be equal to negative of a negative, so that'll be 2.123 times 10 to the 5th joules per mole of copper. All right, well, now we want to get from, we have 50 grams, we don't have 1 mole, so we'll do 50 grams of copper. We'll convert that copper. So let's see, copper here is 63.55. So 63.55 grams of copper per mole of copper. And then we'll multiply by the 2.123 times 10 to the 5th joules per mole of copper. All right, I'll clear all that. We'll do 50. Make sure calculator is on the screen there. Yes. All right, so we'll do 50.0. So 50 divided by 63.55. And then we'll multiply that by 2.123 times 10 to the 5th. And we've got 3 sig figs, so I'm going to put 1.67 times 10 to the 5th joules is going to be our quantity. So what is the work in joules? Well, that is the maximum amount of work. So W max per that 50 grams. Now we want to convert that into kilowatt hours. Our conversion to kilowatt hours we did just a minute ago. So we'll do 1.67 times 10 to the 5th joules. Multiply that by 3.6 times 10 to the 6th joules per kilowatt hour. We're actually dividing by that quantity. So I'm going to take that, just divide by 3.6 times 10 to the 6th. And 3 sig figs, we'll call that 0.0464. So 0.0464 kilowatt hours. And that is our final answer there. So we had that and that. All right. And let me check something real quick. Yes, so that is the end of section 5 in chapter 20. Our next video will start on section 6.